Most people don't fail calculus because they're not smart enough. They fail because someone handed them a page of strange symbols and never told them what those symbols were actually for. It can look like a secret language that nobody hands you a translation for. So today, we fix that. By the end of this video, you are going to understand what calculus really is, why it was invented, and how its two big tools work, all in plain everyday words. No memorizing, no scary formulas, just the ideas, one clear step at a time. Hey, it's Daniel from Simplex Academy, and this is the explanation I wish someone had handed me the very first time I saw the word calculus. If you want more hard topics explained clearly and calmly like this, subscribe to Simplex Academy. It genuinely helps the channel grow, and it means the next subject that scares you gets a whole lot easier too. All right, let's make calculus actually make sense. Here is the first thing nobody tells you. Regular math, the kind you grew up with, is wonderful at things that stay still. If a car drives at 60 miles an hour for 2 hours, you multiply, and you get 120 miles. Clean, simple, done. But now look out the window at the real world. Almost nothing stays still. Your speed goes up and down, prices rise and fall, the temperature drifts all day long. Your phone battery drains fast when you are watching video and slow when it is resting in your pocket. The moment something is constantly changing, that simple multiplication quietly breaks down. You need a different kind of math, one that is built for motion and change. That is calculus. That is the entire reason it was invented. Calculus is just the math we reach for when things refuse to sit still. And really, it all comes down to two simple questions. Question 1. How fast is something changing right now, at this exact moment? Question 2. When something has been changing the whole time, how much has added up in total? The first question is answered by a tool called the derivative. The second is answered by a tool called the integral. 2 questions, 2 tools. If you remember nothing else from this video, remember that, and you are already ahead of most people who sat through an entire semester. Let me make those 2 questions feel real. Picture yourself on a road trip. Question 1, how fast am I going right now? Is the number on your speedometer that jumps every time you touch the pedal. Question 2, how far have I traveled in total? Is the number slowly ticking up on your odometer? Same trip, 2 different things you might want to know. And here is the quiet truth calculus was built for. Your speed was never perfectly steady. So getting from one number to the other is not simple multiplication. That gap between a changing rate and a running total is exactly what calculus crosses. Keep that road trip in mind because we will come back to it. But before those 2 tools, there is one idea holding the whole thing up. It is called a limit. Let's start there, because once limits click, everything else clicks right along with them. Here is the simplest way to picture a limit. Imagine you are walking toward a wall, and with every step you cover only half of the distance that is left. Half, then half of that, then half again. You get closer and closer and closer. You are almost touching it. But with these shrinking half steps, you technically never quite land on it. Now here is the clever question a limit asks. Forget whether you ever truly touch the wall. Where are you obviously heading? You are heading straight to the wall. That destination, the place you are clearly approaching, is the limit. Let me give you a second way to see it, with numbers. Picture a value that goes 0.9, then 0.99, then 0.999, each step adding another 9. Where is it heading? Straight to 1. It may never become an exact one, but the destination is not in doubt. That is the limit. So a limit is not about where you happen to be right now. It is about where you are clearly going. Why does this matter so much? Because in a world of constant change, there are moments you cannot measure head-on. You cannot freeze time and read an exact value, but you can sneak closer and closer and watch what number you are closing in on. A limit lets you name that destination with confidence, heading toward, not landing on. You will need it for both of the tools that come next. Let's meet the first big tool, the derivative. The derivative answers our first question. How fast is something changing right at this instant? Think about driving again. Your whole trip might take an hour, and you could easily work out your average speed for that hour. But that average is not what your speedometer shows you. Your speedometer shows your speed right now, this exact second. Tap the gas, and the needle leaps up. Ease off, and it sinks back down. That little needle is quietly doing calculus for you every second you drive. It is showing you an instant rate of change. That, in one simple picture, is a derivative. Now here is how it secretly leans on a limit. To find your speed at one single frozen instant, you look at how far you traveled over a tiny sliver of time, say 1/10 of a second. Then you shrink that sliver smaller, 1/100th, then 1/1000th, closer and closer to zero, and you watch what number your speed settles toward. That settling toward number is the derivative, the rate of change at one exact point. And here is the part that surprises people. A derivative is not just one lonely number. It is a whole new tool that can hand you the rate of change at every moment. If you start with something that describes where your car is over time, the derivative gives you back a brand new thing that describes how fast your car is moving at every single second of the trip. Position goes in. Speed comes out. That is the derivative's whole job. It takes, how is this changing overall, and turns it into, how fast is this changing right now? Now the second big tool, the integral answers our second question. When something keeps changing, how much adds up in total? Picture filling a bucket from a faucet, but the faucet refuses to hold steady. Sometimes it is a thin trickle, sometimes it gushes, sometimes it slows back down to a drip. You want to know how much water ends up in the bucket. You cannot just multiply one flow rate by the time, because the flow kept changing the entire way through. So what do? You break the time into tiny slices. In each tiny slice, the flow barely changes, so you can estimate the little bit of water that went in during that slice. Then, you add up all of those tiny bits, one after another. Slice by slice, you build the grand total. That adding up of countless tiny pieces is exactly what an integral does. Let me give you a second example. Right back on our road trip. Suppose I never let you see the odometer, but I did record your speed at every moment. How far did you travel? Same trick. Chop the trip into tiny time slices. In each slice, your speed barely changed, so the distance is roughly your speed times that little slice of time. Add up every slice, and you have your total distance. You just integrated your speed to recover your distance. And once more, a limit is hiding quietly inside. You make the slices thinner and thinner, closer to zero width, and the total you are heading toward is the exact answer. So the integral takes a changing rate and tells you the grand total it quietly built up. Let me give you one picture that ties both tools together, because a simple graph makes them obvious. Imagine a curve drawn on a graph, rising and dipping as it moves to the right. The derivative is the steepness of that curve at any point you pick. A steep climb means a big rate of change. A flat stretch means almost no change at all. So the derivative is the slope, how sharply the line is tilting right where you are standing. The integral, on the other hand, is the area trapped underneath that curve. If the curve shows your water flow, the area beneath it is the total water. If the curve shows your speed, the area beneath it is the total distance. One tool reads the slope. The other tool measures the area. Same curve, two different questions, and now you can almost see them with your own eyes. So now you have two tools. The derivative breaks a total down into an instant rate. The integral builds a total up from instant rates. And here is the beautiful part, the idea that ties all of calculus together into one piece. These two tools are opposites. They undo each other. Think about speed and distance one more time. Start with your car's position over time. Take the derivative, and you get its speed at every moment. Now take that speed and integrate it, add it all back up, and you land right back on the position you started from. You went from position to speed and back to position. One tool perfectly unwound exactly what the other tool did, like zipping and then unzipping the very same zipper. That is the fundamental theorem of calculus, and in plain words, it simply says this. Finding a rate and adding up a rate are two sides of the very same coin. They run in opposite directions on the same road. You do not have two random, unrelated tricks to memorize. You have one single relationship looked at from both ends. The day that clicks is the day calculus stops feeling like a messy pile of rules and starts feeling like one clean, simple idea. Let me walk you through one gentle example so you can actually feel it work. Imagine you drop a ball off a balcony and you have a simple rule that tells you how far it has fallen after any number of seconds. After 1 second, it has fallen a little. After 2 seconds, it has fallen quite a bit more, and you can clearly see it is speeding up as it goes. Now I ask you, How fast is the ball moving exactly 2 seconds in? Average speed will not give you the honest answer because the ball keeps accelerating the whole way down. So you do the derivative move. You look at how far it falls between 2 seconds and just a hair after, say, 2 seconds and one tiny extra slice. You measure that small change in distance, then you shrink that extra slice closer and closer to zero, and you watch the speed settle toward one clear number. That number is the ball's exact speed at the 2-second mark. You just found a derivative in plain steps without touching a single scary formula. And if you wanted the reverse, if I handed you the ball's speed at every instant and asked how far it fell in total, you would slice the time up, add the little distances together, and that is your integral. Same ball, 2 questions, 2 tools, working as perfect opposites. Now you might be wondering, where are all the formulas? Here is the honest answer. The formulas are just shortcuts. Once people understood these ideas, they noticed patterns that showed up again and again, and they wrote those patterns down so nobody had to shrink tiny slices by hand every single time. That is all a formula really is. A packaged shortcut for an idea you already understand. When you learn the rules later, they will not feel like magic spells that fell out of the sky. They will feel like sensible little tools that do the slicing and the shrinking for you. Understand the idea first, and the formulas become the easy part. That is, the order school almost always gets backwards. Now let's make this real, because calculus is quietly running your entire day. Your car's speedometer, like we said, is a live derivative. Your GPS does the exact opposite job. As you drive, your speed keeps changing. So to figure out how far you have actually gone, your phone is basically integrating that changing speed over time. The little battery estimate on your phone that says about 3 hours left is a derivative too. It looks at how fast your charge is dropping right now and uses that rate to predict the time you have left. It goes further than that. When an artificial intelligence learns, it is using derivatives to figure out which direction to nudge itself so it makes fewer mistakes over and over, millions of times. Every time a chatbot gives you a sharper answer than it would have a year ago, derivatives did that training. When a doctor decides how often to give a medicine, they are tracking how fast the drug rises and falls in your blood, which is a rate of change, a derivative. Too slow and the medicine stops working, too fast and it becomes unsafe. So that rate genuinely matters. And the interest growing in a savings account, piling up little by little as the balance itself keeps growing, that is an accumulation, an integral. None of this is classroom decoration. It is the quiet machinery behind tools you already trust every single day. Before we wrap up, let me save you from the traps that catch almost every beginner. First mistake. Thinking a limit is the value at a single point. It is not. A limit is the value you are heading toward. Something can clearly head toward a number it never actually reaches, like those 9s creeping toward 1. Always ask, where is this going? Not what is it sitting at right here. Second mistake. Believing you have to memorize a wall of formulas before you can understand anything. That is completely backwards. When you understand what a derivative and an integral are actually doing, the formulas turn into handy shortcuts that make sense. Memorize first, and you will freeze the moment a problem looks even a little different. Understanding first, formulas second. Third mistake. Thinking those tiny slivers of time or width are basically just zero, so they do not matter. They are not zero. They are unimaginably small, but they still carry the whole idea. Treat them as plain nothing, and the logic quietly falls apart in your hands. And the last one, the big one, believing you are simply not a math person. You have been doing rough calculus in your head your entire life. Every time you judged how fast another car was closing in before you changed lanes, or guessed how long your snacks would last on a long drive, you were estimating rates and totals. You were never missing the brain for this. You were only ever missing a clear explanation. So, let's pull it together one more time. Nice and simple. Calculus is the math of things that change. It rests on the limit, the idea of the value you are heading toward. It hands you 2 tools. The derivative tells you how fast something is changing at one exact moment, and on a graph that is the slope. The integral tells you how much has added up in total, and on a graph that is the area underneath. And the fundamental theorem ties them together by saying those 2 tools are simply opposites, one undoing the other. just like speed and distance on your road trip. That is the whole heart of calculus. Everything else you will ever study in it is really just these few ideas wearing different outfits. If this finally made calculus click for you, that is exactly what Simplex Academy was built for. So tell me down in the comments, what is the next subject that has always confused you? Algebra, statistics, physics, something else entirely? Drop it below and I will explain it just like this, from zero with no fluff. I'm Daniel. Thanks for watching and I will see you in the next one.